Okay, so recall the definition of the Laplace transform. It's L of f equals integral from 0 to infinity e to the minus st f dt. So theorem 14, we have to show the Laplace of t to the n equals n factorial over s to the n plus 1, where here n is a can be 1, 2, 3, 4, and so forth. So it's a positive integer. Okay, so to prove this, since we have to prove it for all integers, all positive integers, one and higher, we're going to prove it by induction. Okay, so step one. Okay, so step one would be to prove the n equals 1 case. So when you put 1 in place of n up here, it should just be Laplace of t. So let's write the definition of Laplace of t right here. So the Laplace of t then, so my f up here would be just t. So it's going to be integral 0 to infinity e to the minus st t dt. I can bring the t in front, which I've done here. Then this is an improper integral, since we're going to infinity up here. So I can replace infinity with a b and take limit as b goes to infinity. Now we're going to have to integrate this. It's going to require integration by parts. So let's note down here integration of parts. Okay, so we want to integrate this guy. It's going to require integration by parts. Here's my integration by parts formula. Integral u dv equals uv minus integral v du. And I'm going to let my u equal t here and my dv equal e to the minus st dt. So let me note that here. Okay, so again my u is t, so u is t. That means du dt then is 1. That means then du equals dt. And my dv is e to the minus st dt. So therefore integrating, dv equals this. So integrating both sides, then my v would be, so when you recall here, when you integrate e to the kt, it's going to be e to the kt over k. So here my k is minus s. So therefore my v, when I integrate this, would be e to the minus st over minus s. Okay, so plugging in up here then for my u's and v's. So doing that we get, so we got uv, u is t, v is e to the minus st over minus s, which I have here, minus integral of v, so this guy, du, which is equal to dt. I can bring that minus s out over here and then integrate this guy using this up here. So doing that we get then, so we get this then when I integrate. So pretty much when I integrate the e to the minus st, I'll bring another minus s down there. So you'll have 3 minus signs. So it'll be minus still, and it'll be s squared. So applying this guy here. So we get this guy then. Okay, so I'm out of space, so let me erase a few things and we'll keep going. Okay, so we have our Laplace of t then equals this guy, and by integration of parts, we just found that this guy, the indefinite one, was this guy. And then we're going to evaluate that from 0 to b then. So we're going to put b in place of t and then put 0 in place of t. So doing that we get then. Okay, so plugging b in place of t everywhere and then subtracting, putting 0 in place of t everywhere, we get this. So putting b here, b here, b here, and then subtracting, putting zeros in place of all the t's, we get this. And for this to work, actually, I'm just noticing here, we have to assume that s is greater than 0, because I want that minus sb, I want that to be a negative number to be able to say something about this limit. So let's make an observation here. So note here, let's look at the limit b goes to infinity, b e to the minus sb. So this part here, the numerator. So I can write that as b over e to the sb. And when b goes to infinity, the top will go to infinity, so will the e guy. So it'll be infinity over infinity, which is an indeterminate form. So you can apply L'Hopital's rule in that case. So it means you can take derivative of the top, here the variable that you can think about as b. So the derivative of b with respect to b will be 1. The derivative of e to the sb with respect to b would be s e to the sb. And this limit will be 0. So it means this guy will be 0. That means that this will be 0 right here. And e to the minus sb, that limit will be also 0 because that'll be 1 over e. And that's gone. And e to the 0 is 1. So it looks like this whole thing will be just minus times minus will be plus here. Looks like it'll be 1 over s squared then, this whole thing. So let's write it here. Okay, so we have Laplace transform of t then. So it's just going to be e to the 0 over s squared, which is 1. So it'll be 1 over s squared. And 1 you can write as 1 factorial, and 2 you can write as 1 plus 1. So therefore, this proves the n equals 1 case. Okay, so next. Actually, let me erase a few. Let me erase a few things here, and then we'll keep going. Okay, so here's our proof continued. We've proven the n equals 1 case. Now here's the induction step. We're going to assume statement is true for n minus 1. That would mean then the Laplace transform of t to the n minus 1. So it'll be this formula up here, replacing n with n minus 1. So it'll be n minus 1 factorial over s to the n minus 1 plus 1. So it'll be just s to the n. So need to show that the n case, or the Laplace transform of t to the n, is this guy, follows from this one being true. So this is the induction step. It's kind of like a chain reaction that we're setting up, because if we can show this is true, the induction step would mean that if you can show the one before is true, then the one after is true. So if we've shown 1 is true, that would imply that 2 is true. Then if 2 is true, that would imply that 3 is true, and so forth. So it set up a chain reaction where it would have to be true for all n. Okay, so this is the induction step. So let's see if we can prove this guy from that being true. Okay, so let's write the definition of Laplace transform of t to the n. Okay, so here's my definition of Laplace transform. So it's basically e to the minus st times your function, which is t to the n here, dt, 0 to infinity. Some proper integral, so write it as b up here, limit b goes to infinity. We're going to have to use integration of parts on this, so let me write it here. Okay, so if you apply integration of parts, I won't go through all the details, but you let your u be t to the n, you let your dv be e to the minus st dt, you'll get this. Okay, and this last part has an integral, so I can pull the n and the minus s out, so I can write this whole thing then as t to the n s. Oh, there should be e here. I messed up here. Should be e in this, and e over here. And I can pull the n and the minus s out. That'd be plus then n over s integral t to the n minus 1 e to the minus st. And when I put the limits on this guy here will end up being the Laplace transform of t to the n minus 1. You can check that definition of Laplace transform of t to the n minus 1. Okay, so let's summarize what we have then. I'm out of space, so let me erase a few things and we'll keep going. Okay, so we have then our Laplace transform of t to the n. So making the substitution with our integration of parts, It's going to be this. And as we mentioned already, this part here is the Laplace transform of t to the n minus 1. Let's note that. Okay, so putting b in place of t and putting 0 in place of t here. I claim this whole thing will be 0. Well, that's definitely 0 there. And this one will be 0 also, using L'Hopital's rule like we showed for the n equals 1 case. The same thing will follow. So you'll have then n over s times the Laplace transform of t to the n minus 1, but we're assuming that looks like this. So I can go there. So therefore this will be then n minus 1 factorial over s to the n. So n times n minus 1 factorial would be n factorial, and s times s to the n would be s to the n plus 1. And that's what we're trying to show. So hence claim follows by induction. So hence claim follows by induction, so we're done. So let's leave it there with this video. Okay,